Students, good morning and welcome back to our today's session. So I hope you would have attended your last previous sessions. Okay. So we are discussing about the materials for 3D printing, right? So this earlier we discussed about the various types of engineering materials and what are the common material types that are used in the recent engineering fields, and they about the metals, classification of metals, then polymers, classification of polymers, ceramics, classification of ceramics, composites, and classification of composites. Okay. So with this, we shifted also towards the different material types that is used for a specific process. So this is the overview which you'll be getting here. So FDM, that is the wire form, will be using the raw material, which is mostly of polymers, and SLA will be using liquid form of raw materials, which will be usually polymers. And for selective laser sintering, we'll be using powder form of raw materials, which will be usually polymer, ceramics, and metals. And for selective laser melting, we'll be using powder material, which will be metals. And for binder jetting process, we'll be again be using powder materials as a raw form. And the material types will be polymer, ceramics, and material metals. And for laminate object manufacturing, we'll be using solid form materials, usually in form of polymers and non-metals. Okay. So with this note, we have been discussing about the various FDM materials so far. So in last class, we discussed about these materials, that is ABS, then PLA, nylon, PETG, okay, which is something like a water bottle which you're using, and HIPS, which is of the advanced materials, polycarbonate, polypropylene, and TPU. So these are the usual materials that are most commonly used type of materials, and we discussed about the various material characteristics and their comparison chart. Okay, this is a chart which gives you the various material properties and their comparisons. So we discussed about these nearly 7 parameters, that is ease of printing, visual quality, stress that can withstand, what stretch it could elongate while during its breakage, and impact resistance, and layer adhesion, heat resistance. So such types of based upon these characteristics, we discuss their relationships. Okay, so this is one of the combined relationships, and this is the individual relationship for each and every material most commonly used in fields. Okay. So we discussed this during last class, and we discussed also about the PVA material, which is a water dissolvable material, most and primarily used for as a support material in FDM processes. Okay, and also finally we touch upon the composites. Here the composites is like carbon filled with the polymers. Okay, so the polymers will be carbon filled, metal filled, and wood filled. Actually, these won't be looking like the actual composites. Only the finishing will be like carbon fiber finish, metal finish, and wooden finish. Okay, whereas their properties will be similar to that of a polymers. That is PLA. Mostly these carbon, metal powders, wood powders, fine, very fine powders will be mixed with the PLA material. Okay, that will be usual content, and within which you'll be mixing the wooden powders and metal powders or carbon fiber. Okay. So with this, till this we have been discussing about last class. Right. So today we'll be seeing about the one of the very most advanced and the now the hot topic in the 3D printing, that is bio extrusion. Okay. So this bio extrusion is done using the FDM process, fused deposition modeling. So this is the actual FDM process. Only thing is you will be using a biocompatible material as the raw material. Okay, so there are a variety of biocompatible or biodegradable components. Mostly PLA is one of the very much biodegradable biocompatible material. PLA, okay, polylactic acid. So that is being used now for developing or printing biological related components, such as like you can see here. So here there is a picture which shows you the how an ear is getting printed. Okay, so this is this is an, uh, a 3D model which you're looking at here. That is, when you're looking at this on the right end, you can see the actual shape of the ears which is getting printed. Okay, so this such a type of technology is now getting into actual applications. So actually, there are cases wherein the certain parts of the injured body. So if someone is getting hit by, someone is getting injured in an accident, and he is sometimes losing some part of his skull or jaw, there are techniques which is primarily called as this FDM technique, fish deposition modeling 3D printing technique, is used to model the injured jaw or the skull part, okay, print it using the biocompatible material, and they'll be implanting into the actual humans. Okay, so this is now the actual applications of this FDM process, primarily FDM process. Okay, there are also other method. There are also other uh, techniques like SLM are also being used, but this FDM is most primarily used. Okay, and you will be, if you want to have more insight about this, please Google it and see. You'll be finding fabulous and mesmerizing products that can be done using this bio-extrusion process. So bio-extrusion is nothing but FDM is always is using an extrusion process. But if you are using a biocompatible material as the raw material, it becomes bio-extrusion. That's it. Okay. So the applications here are surgical models for preoperative surgical operations. So this is the surgical models, okay, and dental fixtures, bridges, and crowns. So the dental fixtures are nothing but the fixtures are used to mold your teeth. Okay, if someone is having injured their teeth now, they'll be each the size of the teeth will be varying from patient to patient. Okay, so they'll be modeling the teeth as like which is has to be fit into his jaw. They'll be modeling it, and they'll be getting the mold cavity using this bioextrusion. Okay, and then within the they'll be casting the teeth. There are also techniques wherein you can directly print the teeth using ceramic printers, okay, and customized patient-specific implants and processes. So this is what I'm telling. Implants, okay, implants like ears or jaw parts or the skull parts. Also, prosthesis nothing but these bones. Okay, if it getting a bones is very get highly damaged. If it is getting broken into number of pieces which can't be when given together. So there are materials which can be used to print the bones actually, okay, using ceramic materials. And live tissue scaffolds for tissue engineering regenerative medicine. So this tissue engineering is one of the very first application of this bioextrusion. Okay, when we'll be getting scaffolds. Scaffolds nothing but the containers which will be used to develop the tissues. The tissues will be developing or living inside, growing inside it. That is called scaffolds. You can, if you need more insight, you can browse it and see, Google it. Okay. So these are a variety of biomaterials that are widely used in uh, these bio-extrusion process. These metals and metal alloys are mostly used, not used in the FDM process, but they are using selective laser melting. Okay. So just I am given this overview in order to give you an idea of how these materials are getting used in the biological applications. Okay. These metals and metal alloys, obviously, you know, the metals and metal alloys are have high material strength, and they can easily fabricate and sterilize. The sterilization is, I hope everyone know what is the meaning of sterilization. Yes. So they can be sterilized, but there are a few materials which can't be sterilized due to their reaction between the oxygens and the water molecules. So the application, moreover, this is what I need to emphasize here: orthopedic implants, screw pins, and plates. So all the orthopedic implants can be done using this platinum, titanium, steel, chromium, cobalt. Usually they'll be using steel, but steel is very uh, high, very high strength, but it has having a high weight, so it is very difficult. So there, these metals are now being replaced by ceramics. Okay, ceramics and carbon compounds, they have high metal strength. Of course, they have a good bio capability. Okay, so they are also used for bioactive orthopedic implants, dental implants, artificial hearing aids. Okay, so this artificial hearing aids nothing but the hearing aids which will be used by the deaf people. Usually, this hearing aids, the shape of the hearing aids will be varying from patient to patient depending upon their shape of their ears. Okay, so earlier they were having only a standard size, which was very difficult to use by all the categories of people. But whereas now these hearing aids can be designed and created a 3D printed depending upon the shape of their ears. Okay, so this is one of the very much fruitful result of this 3D printing, biocompatible 3D printing. And of course, the polymers. Always these polymers like PMMA, these PMMA is nothing but polymethyl methacrylate, which is given at the bottom, and polycarbolactane and PLA called polycarbonates, polyurethanes. So these polymers are biodegradable and biocompatible. So these are the one which are most widely used for processes, tissue engineering scaffolds, and drug delivery systems. Okay, but they won't be used into the actual implants because they are very finding very hard to sterilize. Okay, but when I come into this composites, they have a variety of implant applications. Okay, so like a dental filling composites, carbon fiber reinforced composites. Okay, so these composites have excellent material properties, and they are also corrosion resistance. So these advantages makes them to be a suitable for porous orthopedic implants, like dental fillings and gloves. Okay, but they are expensive. So this is an overview to give about these biomaterials and their classifications. But this is just an additional info to me. Okay. So far we were discussing about the various types of FDM materials that are available. Okay. And now let us get into the next topic, that is SLA. Okay. So in FDM materials, the form of liquid will be in the form of the raw material will be in a wire form. Okay, but it will be solid, a solid wire form. Okay. Whereas here in SLA, that is stereolithography, you will be having the materials in the liquid form. So here you can see. So if you're something fascinated about do-it-yourself videos, you can see many of them will be using these resins. I hope you would have seen in YouTube or Facebook. They'll be using these resins to create beautiful artifacts. Okay, I hope someone would have gone through those videos. So that is called as a resin. Okay, it will be in a liquid form. Usually these resins are thermoset photopolymers. Okay, that solidifies and exposed to the light, producing high detail parts with smooth injection, more like surface finish. Okay, so this is the resin. So the resins will be in the liquid form. So this photopolymers we have already discussed during the uh, classes on SLA. Okay, we have discussed about the process called as a photopolymerization. Okay, so that is why we have already discussed this photopolymers. So when it's getting exposed to light, most prominently UV light, okay, ultraviolet light or laser lights, they'll transfer from liquid to solid. So only the area where the light is, where the photopolymers are exposed to light, only those molecules will be converting from liquid to solid. Okay. So there's nothing. Why it is getting liquid to solid means usually in liquid the distance between the molecules will be large. Okay, that is why it is called as liquid. Okay, the distance between two molecules will be large. So when this light is getting exposed onto it, these molecules will get attracted to each other. Okay, so that the distance between their molecules will be made very minimal. Okay, so that is the case. That is the reason why it is turning from liquid to solid. Okay, usually this liquid resin is a mixture of organic compounds. So the most common type of resin which is used is epoxy resins. Okay, rather is called as polyepoxies. So this is a class of reactive prepolymers and polymers which contain epoxy groups. So these epoxy resins are formed from an oligomer containing at least two epoxy groups and a curing agent. So curing agent will be within itself. So this curing agent will be responsible for their close attraction. Okay, so usually these epoxy resins can be UV cured using your ultraviolet. So if ultraviolet rays is getting instead on these epoxy resins, they'll be turning from liquid to solid. Okay. So there are variety of resins that are available, but only a few selected resins types will be used as the materials for this SLA process. Okay, so this is the standard resin. First is usually called a standard resin, so which will be having a high Euclid features and smooth surface finish. Okay, and also going to get a wide assortment of color choices. You can get wide color choices, but the problem is it is a brittle. So it will be very brittle. So it will be used suitable only for prototyping. It can't be used for functional prototypes. So this here you can see one of the person which is sitting on a funny video where he's sitting on the riding a dinosaur. Okay. So here this is made of a standard resin. Okay. So it can also be, you can also set the properties so that whether it could be a transparent one or an opaque one. So you can give the define the densities that could be filled, and you can also set these transparency areas. Okay. And next step is durable resin. So this durable resin or tough resins, sometimes called as tough resins, have these properties of ABS and PP. PP is polypropylene plastics. Okay, they have the combined property of ABS and polypropylene. So ABS is having a high mechanical strength, whereas PP is having a good flexibility. So when you're using these durable resins, it will be having a good strength and it will be also flexible. Okay, so there is this will be allowing the metal printed parts using this durable resin will be having greater strength, high toughness, and high durability. Okay, when compared to the standard resins. Okay, so these durable parts printed using this durable resins are suitable for functional prototype. Yes, so you can also use consumer goods, and generally low friction and low wear mechanical parts can be printed using this durable resins. Okay, and this PP like resin is has also semi-flexible properties. Okay, it can it can be flexible to a certain limit. Okay, and is ideal for slab fit application. Slab fit is nothing but to have a good example of slab fit, the earbuds which are having in your headphone or earphones. Okay, so if you are pressing it, it will be getting fixed into the earpod. Okay, so that is a snap fit. So that such a kind of applications can be done applied using your durable resist, but they have low thermal resistance, so they can't be used for high temperature applications. These durable resists. Okay. Next is a rubber-like resins. So this has the name in place. The rubber-like is nothing but it will be actually looking like a soft rubber feel. So if you're printing some materials using this rubber-like resin, you'll be getting a very flexible parts, so that it will be looking like soft rubber-like feel. So here at the right side top one, you can see some of the products or which has been printed using the rubber-like resin. So this heart and some of these points. Okay, these are all been printed using rubber-like resins. So this rubber-like resin can be compressed, print, making it good choice for usable models, wearable prototypes, grips and handles, and also fashion and jewelry applications. So it has very wide variety of applications which are possible using rubber-like resins. So, however, it should not be noted that the properties of rubber-like resin cannot be compared to rubber. So, the property which they are talking here is about the expanding nature. So, you can see rubbers can be stretched to a larger amount of length. But whereas these rubber-like resins have very limited strength, stretching areas. Okay. Next. And so these are the rubber like resins. So these are the various types of SLA materials most commonly used. And the other common materials are high temperature resins. Okay, so this high temperature resins, they are resins which have high heat resistance. So it can also be exposed to about 200 degrees Celsius. So they have very high thermal properties. So this is the reason they will be used for injection molding and thermoproofing of jigs and fixtures. So this is very much mechanical kind of application. Next is castable resin. Okay, resins which can be casted, the property can be casted. Okay, so this is a cost-effective choice for production of intricate patterns for investment or casting. That is the jewelry casting. Investment casting is nothing but the casting process used for jewelry only. So here you can see on the top there is a ring which is getting done. So this blue one is the molding used done using your casting castable resin. Okay, inside which you can pour the molten metals, which can be finally taken out with this the actual ring. The blue is the 3D printed part, which is being used to get this mold ring, which is in the silver ring. Okay, so this type of intricate shapes, you can see how the details are here. So such a type of details is can be produced using this castable process. Okay, usually this will be made of wax. Okay, a ceramic mold which made about a wax pattern. Okay, so after it is getting solidified, if you are heating the wax, it will be getting cooled down. So it will be can be easily taken. So next is dental and medical resins. Okay, so these resins is biocompatible. Obviously, the name itself implies dental and medical means it must be having biocompatibility. Okay, so mostly they are used for dental applications. So here you can see in the top, you can see a dental application wherein the lower jaw is being molded. Okay, so also this is can be used for the custom fitted hearing aids and surgical aids. Okay. And parts printed with these resins can be steam sterilized for direct use in the operation room. Yes, of course, it can be steam sterilized. So only the sterilized particles can be used for the biological applications. And also there is an option for long-term point-able compatible dental resin, which can be used in orthodontic devices designed for longer contact with human bone. So if you want to reform your teeth or like something like that, you need to have the models and shapes. Okay, so those devices will be there fitted into your mouth. So you can if you are having these there are variety of parts wherein you have to guide your teeth growth. So for example, for 5 months or 6 months, they have to use the clip. Okay, so those clips which are getting used must be having biocompatibility, and those clips must be designed based upon the patient's mouth design. Okay. So such a type of applications will be using these resins. Okay. And next is this is one of the new SLM material which has been developed recently, that is a ceramic filled resin. Okay, so you'll be finding a silica filled polyphotopolymer which has high strength and rigidity, creating parts with very smooth surfaces and fine features. So on the right top, you can see an object which has been printed using this ceramic filled resin. Okay, so these can also be heat treated. You can fire it and kiln is nothing but a heater. Okay, it can also burn. So these are the various types of SLA materials. Okay, so let us have a small recap here. So the various types of SLA materials are standard resins. Okay, which is the most widely used. Then is durable resins. Okay, durable resins have they have tough and they simulate the properties of ABS and polypropylene thermoplastics. Okay, they have the combination of both these properties, ABS and PP. Okay, then is a rubber-like resin. So the rubber-like resin is something which will be giving a soft rubber-like feel, very soft, and it can be a stretchable to a certain limit, but it can't actually replace the properties of a true real rubber. Okay, it will be having the say for example we can say 50% of the properties of a true rubber. Okay. Next is high temperature resins. Okay. This type of resins exhibit high heat resistance. Okay, it can work up over 20 degree, 200 degrees Celsius. Next is castable resin. Okay, then is which is used for this jewelry applications. Next is dental and medical resins, which is a which has a biocompatible properties and can be used for dental and medical applications as well. Okay. So next is the new metal which is getting developed as ceramic build resin, which can be heat treated, which has a high heat resistance. Okay. So these are SLA materials. So when you're comparing the FDM and SLA, usually the FDM is the process which has a wide variety of applications. Okay, so whenever you're talking about the FDM and the other processes, usually FDM will be having variety of material choices. Okay, since it is a polymer and it is a wire based, you can easily make wires out of it. But getting the resins is very difficult. That is why you will be finding when you're comparing SLA and FDM, SLA will be having low material choices. When you're comparing SLA with the other, that is SLM and SLS, will be still those SLM and SLS will be having still low material choices. Okay. Right. So this is as far as the SLA is concerned. So next we'll be talking about the materials for SLS and SLM. So SLS is selective laser sintering and SLM is selective laser melting. So both these process will be using the materials in powder form with very fine grain sizes. Okay, the powder sizes will be in the forms of microns. All right, so they'll be using powder forms. Obviously, the another technique, that is binder jetting, will also use powder form. Yes, of course, which we'll be discussing in their later classes. Okay, so this is selective laser sintering. Yeah, I already told you what is sintering, the difference between sintering and melting. So in sintering, you won't be converting the entire powder into liquid. Only you will be increasing the temperature to a sintering temperature, which is normally 2/3 of the melting point of the material which is used. So that only the boundaries will get attached to each other, not the entire powder particles. Okay, that is what sintering is. Whereas melting is, the entire powder particles will be converted into solid to liquid. So it will be forming a liquid mixture. Okay, so that is difference between a sintering and melting. So when you're talking about sintering, we'll be using polymers, ceramics, and metals, and even polymers is in form of composites, ceramics in forms of composites, and metals in form of composites. So all these three choices are possible when you are using a selective laser sintering process. Okay, but the most commonly used type is polymers. So mostly the polymers are used. Then polymers will be using only thermoplastics. So I have already told you during the classification of plastics, it can be divided into thermoplastics and thermosets. So thermosets is something like you can't reuse. Okay, whereas thermoplastic you can reuse and you can reshape easily. Again, these thermoplastics are of two categories we have already discussed in earlier classes, that is amorphous and crystalline. So both these type of forms are used depending upon the application which is required. Okay. Whereas when we are talking about this ceramics and metals, usually the ceramics and metal powders will be having a thermoplastic binder coated or binder mix. So over the powder particles of ceramics and metals, we will be coating it with a thermoplastic binder. So when an sintering process is happening, only this thermoplastic binder will form into a semi-solid and get attached to each other, so that the ceramic and metal powders will also get joined. So this is the way in which you will be using your ceramics and metal powders for this selective laser sintering, whereas you won't be altering the shape of the metals or ceramic powder particles, never. Okay, so that is why I told you we will be using only the polymers, most prominently the polymers. Okay, and variety of polymer composites, which will be discussing in the next slides. Okay, whereas when you're coming for selective laser melting, here you'll be using the metals and composites, ceramics and composites. So here you can have a wide variety. So in metals you'll be finding things like as steels, variety of steels, copper, sometimes bronze, aluminums are also used. Whereas in ceramics and composites, there are also other ceramic composites are also employed, which we'll be discussing in our later classes. Okay. So now let us see about the SLS materials. So I already told you SLS material will be using only the polymers and their composites. Okay. Now, so the most common material for selective laser sintering is nylon. So please remember this very carefully. Okay. The most common material for SLS is nylon. It is a popular engineering thermoplastic material. Again, it is a thermoplastic material. It has a lightweight, strong, and flexible properties. So all these are the most favorable properties that is you can be used for a SLS process. Okay. So nylon has stable against impact. Yes, it can. It has a high impact resistance, chemical resistance, heat resistance, UV light, water, and dirt. So all these resistance this nylon is having. So that is why it is very much suitable for your rapid product. This nylon is also used in FDM process as well. So I hope if you can remember well, this nylon is also used in FDM process also. Okay. Whereas here you are using this in the form of a polyamides. So here you can see nylon is a synthetic thermoplastic polymer that belongs to the family of polyamides. Okay, so very polyamides is nothing but nylon is a polyamide. That's it. So you don't get confused. Okay. So there are two versions of commercially used things for this nylon. That is nylon 11 and nylon 12. Okay, so nylon 11 or they'll be calling it as PA11, or as nylon 12 they'll be calling it as PA12. Okay, so these are the material types which have been developed exclusively for this selective laser sintering process. Okay, so both are similar. Both these PA11 and PA12 are similar in material properties, but this PA11 is slightly more flexible and impact resistance when compared to the PA12, whereas PA12 is more stronger and has good abrasion resistance, and it is a biocompatible. So whenever you're talking about biocompatible, yes, it can be used for biological applications. Okay. So here you can see one of the table which you can have a relative characteristics between these nylon PA12 and nylon PA11. So when I talk about the strength, so both are having slightly the similar strength values. So here the nylon PA12 is having 50 megapascal, whereas the nylon PA11 is having 48 megapascal. Okay, both are more or less the same. But looking about the Young's modulus, so the nylon is having higher Young's modulus. But on the contrary, if you are seeing the elongation, nylon PA12 is having 12% of elongation, whereas nylon PA11 is having 35%. It means it can elongate, it can be stretched to a longer extent than the PA12. Okay, nylon strength is external, but at the the contrary, it is having a low strength, whereas it is having high strength. Obviously, if you can see, if you are when it is getting extended, now it is having a low strength. Okay, so that is what the relationship which you have to pick it here from this table. Okay. So this is about your nylon, and of course these nylon 12 and nylon 11 are single component powders. Single component is nothing but they will be having the only one. If you are using nylon 11 alone, the all your powders must be of nylon 11. You can't mix it. But there are printers, SLS printers, which are now being used, which has two component powder capability. Okay, something like that. Okay, so nylon 11 will be coated over nylon 12. So such as coated powders are powder mixtures. Okay, or nylon 12 will be coated over nylon 11. So these are the variety of ways in which you can manufacture the powders in such a way like this. And of course, nylon composites also being used with aluminated carbon or glass are developed to optimize the parts for higher strength. So within this nylon 11 and 12, you can also add aluminide also into it, which will be increasing the capacity. And if we can also add carbon into the nylons, which will be increasing its strength. And you can add glass into it, which will be increasing stiffness. Okay. So these variety of options are available. Okay, so you can see some of the parts which are printed using the nylon 11 and 12. Now, so the other materials I told you here. Earlier I told so these nylon composites. Okay, so the nylon composites is this the composite materials for these polymers. Nothing but aluminum filled nylon, that is called as alumide. Okay, so it will be having a metallic appearance. So this part is an alumide part which is being printed here. It has a metallic appearance and has a good stiffness. Okay, this is aluminum filled nylon, that is alumide. And if you are filling glass into the nylon, it is called as PAGF, the commercial name. It has a high stiffness. This white color thing which is on the right top is a glass filled nylon part. Okay, it has a high stiffness, high wear and temperature resistance. Since glass is fixed on it, this glass will be having higher wear and temperature resistance, which will be also making the entire part to be very high and very wear and temperature resistance. But the problem is anisotropic behavior. So this anisotropy, I will be discussing it in the last class. Okay. So this is very important property behavior of all the 3D printed parts. I will be discussing it in the last. Okay. But it is very important. Okay. Now, next is carbon fiber filled nylon. So within this nylon, you can fill the carbon fibers. So excellent stiffness you can get. So this right side, this is the black part. This one is a carbon fiber filled nylon. Okay, it has a high weight to strength ratio. So high weight to strength ratio is nothing but when you are using the actual, say for example, if you are having weight of a strength, it will be having the strength of a steel and the weight of an plastic. So that is the how the combination of these properties are. Okay, so strength of a steel and weight of a plastic. So that is how you can explain the properties of this carbon filled nylon. Of course, it is highly anisotropic. Okay. And next, one of the very latest development in the material side is this TP, that is thermoplastic urethane powder. Okay, so this is a fine powder based on thermoplastic urethane, specially formatted to function on laser sinter. Okay. So it enables the manufacturing prototypes, presentation of functional parts in elastomeric plastic. So far we are discussing about only thermoplastics. So in the definition, in the classification, I have been discussing into two categories. That is, one is your thermoplastics, another one is the elastomers. Okay. Elastomers is nothing but which can have a good elasticity. It can be stretched like an actual rubber and can be contracted, and while releasing it will be retaining its original shape and size. Okay, so one such material is thermoplastic urethane powder, which will be used to create or print good high detail resolution and good mechanical resistance, flexible and smooth prototypes. So here you can see the man is holding an printed mesh using the TPU material. So look at here how is he compressing it. So if he is releasing it, it will be regaining its original shape. Okay. So this way we can uh, print this elastomeric materials also. Okay. So these are your variety of materials now. So let me have a small recap here. Okay. So nylon. So nylon will be having two types. That is nylon 11 and nylon 12. Nylon 11 is something called as PA11 and nylon 12 is sometimes called as PA2. Okay. So these are the material properties for it, and these nylons can be combined with aluminum to form alumides, and also combined with the glass filled nylon, carbon filled nylon, and the latest development is thermoplastic urethane powders. Okay, so this is the SLX material guide. Okay, so these cast form, duraform, all these are the materials or the material names used by the actual company. So these are names of brand names. Okay, so this you can have a recap wherein you can use, say for example, if you are using duraform, means that is TPU, it is having a material color of white. So and this has a high elongation. So this symbol denotes it as a good elongation. And of course, this means this also it has a elastomeric rubber-like material. Okay. So this way you can differentiate. So this blue color means it is a thermoplastic. If it is an orange color, it is a polystyrene. If it is a blue color like this, it is a nylon. If it is a black color, it is nylon 11. This is nylon 12. So this way you can get the relationship between the applications or the material selection guide. So if you want a particular material to be a high elongated material, you have to go for Duraflex or Duraform. Okay, if you have high temperature resistance, you have to go for Duraform Pro X. Okay, also Duraform HST. So this way you can select the materials. Okay, right. So as far as today's class is concerned, this is enough. Okay, so if you got any doubts,